Hello, ladies and gentlemen. It's a pleasure for me, Tom, to give our presentation for you. The title of our paper is Speech-to-Stroke: Generate Chinese character strokes directly from speech. Our main work is to propose speech-to-stroke. A novel model exploits and utilizes the phonetic information in Chinese characters. To start with, let me introduce the theoretical foundation of our work. About 80% Chinese characters, they are all pictographic compound. Pictographic compound means this character is made up of two parts: the semantic component, which delivers semantic information, and the phonetic component, which delivers the pronunciation of this character. Take this character you as an example. The left part means water in Chinese. Infers that this character represents a kind of liquid. The right part is character you, sharing the same pronunciation with the whole character you. Thus, we know the structure of a Chinese character carries its information, semantic information and phonetic information. There is already some research on this internal structure feature, proving its effectiveness on Chinese NLP tasks. However, existing research, they all concentrate on the semantic information, and they just neglect the phonetic information. Therefore, we were inspired. How can we use the phonetic information in Chinese characters? On this question, our answer is strokes. To be specific, is strokes order sequence. Now, I'd like to elaborate our work from three questions. What did we do? Why we do so? How do we do that? The first question, what did we do? We propose a model generating stroke sequence directly from speech. Then we can decompile this sequence into Chinese characters. I have talked about stroke many times, so what is stroke? Stroke is the minimal unit in a character. As we see, the capital A has 3 strokes, and this Chinese character Da has 3 strokes too. Now, let's move to next question. Why we specially convert speech to strokes rather than doing a normal speech recognition? As we all know, in English, the minimal meaningful unit, or we say morpheme, is usually a word, just like this word strawberry. A word is made up by several letters, so the letters are the minimal unit of a word. As I mentioned above, strokes are the minimal units of a Chinese character, but in Chinese, the minimal meaningful unit can be a single word, a single character. That means the corresponding component of an English letter should be a Chinese stroke rather than a Chinese character. There are 26 letters in English, so when we do NLP tasks in English, we only need a small character set, or we say vocabulary. But on Chinese NLP tasks, usually we use a big vocabulary, including thousands of characters. Fortunately, almost all Chinese characters are made up by 32 kinds of strokes. If we regard strokes as letters, then we get a vocabulary of 32, reducing the scale extremely. Previous research on strokes, they just used 5 categories to classify strokes. Our method has finer granularity by contrast. Another reason we use strokes is the aforementioned internal structural phonetic information. English words, they belong to phonogram, while Chinese characters are typical logogram. By converting characters into stroke sequences, Chinese can become phonogram to some extent. Obviously, phonogram has advantages on speech recognition. We can see all these 5 words all have a shen in it, so they share a tion in their spelling. In the same way, all these 5 characters, they are pronounced as lun, and they share a common substring in their stroke sequences. Due to this transformation, we can obtain the vocal feature from the character directly. Other extra phonetic information like pinyin is not needed anymore. This is the overall architecture of our model. Our model has 2 parts. First, we pre-treat our dataset by decomposing characters into strokes. Another part, just like a regular speech encoder, well, it's predicting a sequence of strokes rather than a sequence of characters. These are the procedures we decompose characters. First, we take a word, divide this word to characters, and retrieve these characters to strokes. There is an official guide of the strokes order of all Chinese characters. We use it to convert Chinese characters into strokes. Then we use number ID to represent all these 32 kinds of strokes for convenience. This is the architecture of speech encoder. Suppose the sequence of acoustic feature vectors is X, and Y denotes a stroke sequence. Our model's goal is to find the most likely stroke sequence Y mark, while X is input. The input of encoder is spectrogram of power. At each output time step, the model makes a prediction. In the bottom of the decoder, there are 2 convolutional layers, applying time and frequency 2-dimension convolution operations. This is because we regard spectrogram as a picture. This kind of structure can capture the frequency and temporal features together to preserve more vocal characteristics. Over convolutional layers is 1 or more bidirectional recurrent layers. We all know that complex recurrent unit is better on long-time dependence tasks, so we apply LSTM units or GRU in these layers. After recurrent layers is a fully connected layer to adjust output dimension, and then is a softmax layer. The parameters of the speech encoder are updated through the backpropagation through time algorithm. We use connectionist temporal classification loss function, a popular method for end-to-end sequence learning, as our cost function. For decoding, we use greedy decoding and beam search. Our dataset includes two parts: a self-built Chinese strokes dataset, including over 20,000 characters and their strokes order sequences. AI Cell 1, an open-source Mandarin speech corpus. Models are implemented with PyTorch, and the stochastic gradient descent is applied during training. For more details of setup, you can check our paper. To the best of our knowledge, our work is the first one to make a speech-to-strokes model. Therefore, there is no standard metric to evaluate such a model. Inspired by the word and error rate, the metric of ASR, we defined the stroke error rate (SER) as our metric. NS is the number of strokes in the reference, while SS, DS, and IS they are a number of strokes with three different kinds of error, which is substitution, deletion, and insertion. The larger the SER, the more different between the two stroke sequences. We tried different types of RNN for our model. All these results are obtained by beam search with the size of 32. The convolutional layers and the fully connected layers are fixed. This is because CNN is used to extract the features of spectrogram, and the last year a fully connected network is used for dimensional adaptation. The core of model is the bi-RNN blocks, which model the temporal connection. As the table shows, the model using GRU has better performance than the other two. The SER of vanilla RNN is particularly high, due to vanilla RNN is hard to cope with long-time dependence. This table shows SER while applying different layers. We can see that when there is 5 recurrent layers, the model performs best. The number of layers increases to 7, the performance degrades. It seems that overfitting occurs. This table shows the results of different beam size. Gradient decoding is identical to beam size 1. We can see that larger beam size improves performance, but time consumption also increases. A balance needs to be found. We randomly pick up 2 results, including the input audio and their output. We decompiled stroke sequence into characters manually. The results shows that our model can capture the connection between speech and strokes effectively. One more thing. Look at this word, 投资, which means investment. This word is a pictographic word. It is determined correctly. Then the word after it, 公司, which means company, is determined, while company is not a pictographic word. This is because investment is related to companies semantically, so the company could be determined correctly. In conclusion, we propose a novel model proving the connection between speech and strokes. We believe that our research will give a new view to the Chinese speech research and Chinese speech recognition. That's all about our presentation. Thank you for your listening.
Hello, my name is Lu Binghan. I'm a graduate student at Xi'an Jiaotong University. The topic I'm going to present to you today is titled as TIBE, CSI Lossless Compression for Multi-User MIMO Network. This is the outline of today's presentation, including the background of this research, the optimization scheme to deal with problems, experimental analysis, and the conclusion. First, I would like to introduce the background of this work. Nowadays, wireless network has been facing the growing demand of higher speed and more efficiency for the mass real-time data transmission among interconnected and intercommunicated multi-users. Multi-user, multiple input, and multiple output technology is being employed in many network infrastructures for future work such as Wi-Fi 6 and 5G. We call multi-user multiple input and multiple output multi-user MIMO for short. In multi-user MIMO system, users can report the estimation of their corresponding channel state information, which we call CSI for short, to access point, and the access point selects the concurrent users with strong channel orthogonality accordingly to maximize the total channel capacity. CSI is a comprehensive metric of the energy attenuation and the phase delay of wireless signal in multipath channel with frequency selective fitting. However, CSI feedback introduces high superfluous channel overhead, which constrains the network performance gained from multi-user MIMO technology. To address the performance degradation of multi-user MIMO network, existing solutions try to reduce unnecessary CSI feedbacks. Most of the methods are focused to reduce the volume of a complicated CSI matrix or reduce CSI feedback times. But if not considering the variance and the fluctuation of real-time CSI effectiveness, blindly reducing feedback is often counterproductive and even aggravate the network performance deterioration. To maintain this type of channel overhead in multi-user MIMO system, current CSI feedback reduction methods mainly fall into two categories: channel feedback volume compression, or CSI feedback times reduction. On the one hand, different compression methods are available to reduce the volume of CSI like CSI-SF, AFC, etc. Such compression methods sacrifice the CSI quality to save channel overhead, but inaccurate CSI may degrade the network performance in turn when faced with multipath effort. On the other hand, various CSI feedback mechanisms are designed to reduce CSI feedback times, like GCC, RAW-PHY, etc. Unfortunately, these strategies cannot prevent the real-time CSI from accumulative error drifting over time. Although these methods can eliminate CSI feedback overhead significantly, they cannot obtain a good signal interface noise ratio. In a word, this approach has not considered the necessity for lossless CSI feedback or the role of historical CSI symbols. Therefore, this paper combined the current CSI symbol analysis with the historical CSI symbol, so as to reduce the unnecessary CSI feedback overhead when considered the effectiveness of the real-time CSI. In this section, we proposed a CSI timeliness-aware balanced mechanism, which we call TAB for short, to compress CSI while keeping its quality at the same time. To reduce unnecessary channel sounding overhead, TAB combines CSI reporting accession estimation method, channel coherence time prediction method, and multi-user balanced scheduling method. TAB leverages a novel update operation on CSI matrix list. It includes both access point and client protocol adjustment, while the sampling form and window size are different. First of all, we need to reduce unnecessary CSI feedback. On the one hand, by the user side, we can estimate the t-distribution of two training frame symbol adjacent to time, and we believe that when the t-distribution value is less than 2.576, there is a 99% confidence probability that the real-time CSI has no significant change. Now the user can use a lightweight egg instead of a CSI for feedback to enable historical CSI reuse. At the same time, a new historical training frame symbol is formed after the current training frame symbol is accumulated to the historical training frame symbol, and the historical training frame symbol is overridden until the CSI update, so as to avoid the problem of CSI error drifting over time. On the other hand, on the access point side, if the same CSI validity period can be properly planned, a necessary CSI request overhead can also be reduced. Through the analysis of recorded CSI symbols, it is found that the corresponding CSI amplitude will show corresponding quasi-standing wave characteristics when the user's equipment is in motion. Therefore, time frequency analysis is used to process the amplitude of CSI symbols over a period of time. According to the obtained power density distribution, the channel fluctuation state can be judged effectively. When the power density tends to a certain characteristic frequency, we can estimate the equivalent motion speed of the corresponding equipment. According to the equivalent motion speed of the device, the CSI validity period of the corresponding user, namely the channel coherence time, can be further estimated. As shown in the figure, at the normal human walking speed, the channel coherence time is far beyond the time limit of sending a packet stipulated by the standard protocol. Therefore, we can effectively predict the coherence time of current channel CSI by using piecewise cubic Hermit interpolation method, according to the equivalent device speed obtained above. However, after such processing, users with long channel coherence time may always occupy the channel, while other users have little or no chance to get the service. So, the corresponding upper limit of service time should be set for the users with different channel coherence time. On the one hand, users with similar channel coherence time are divided into the same group. Each group sets the corresponding maximum time slice to limit the maximum user's service time. At the same time, for users with high channel quality, access point will choose the service first. We adopt short runtime job first algorithm to reduce the average waiting and turnaround time during user scheduling. So far, the CSI reporting accession estimation method, channel coherence time prediction method, and multi-user balanced scheduling method are integrated into one, which exactly constitutes the CSI balanced compression mechanism of TAP protocol. As a result, unnecessary CSI requests and reports can be controlled, and the active users can be properly scheduled. This topic realized multi-user MIMO network through USRP hardware and software platform. All network devices work under the same line and have different IPs. To ensure accurate clock synchronization, all USRPs share an external clock source. The entire system is compatible with the 802.11 ACAX protocol, Quick protocol, and standard MIMO specifications, including the modulation and code rates. Therefore, TAP can be easily implemented on commercial off-the-shelf network interface cards without hardware modification, such as Intel 5300 network interface card. TAP implements orthogonal frequency division multiplexing modulation, packet detection, channel estimation, and symbol demodulation. We use LabVIEW to achieve orthogonal frequency division multiplexing and channel estimation in the prototype system based on USRP. Besides, we have obtained some micro-benchmark results and the overall performance using Intel 5300 network interface card with 4-axis motion testbed as the figure shows above. Moreover, to verify our methods, we examined type in 3 different scenarios with general multipath as shown in corridor, office, and workshop. We evaluated the effectiveness of reusing CSI within channel coherence time. To illustrate this point, we first verified the performance of type in reducing CSI feedback overhead. The figure shows that the average number of CSI feedback times for continuous 100 rounds of uplink and downlink multi-user MIMO transmission in tab respectively, and the average number of CSI feedback times in uplink increases with the growth of number of users' AP's attendance. Obviously, feedback overhead can be significantly reduced by leveraging CSI reuse, as they only need less than 4 times of feedback for 100 rounds. When the user population reached 5 times of the number of AP's attendance, the average CSI feedback times would be close to 70% of number of AP's attendance, which means the performance of type begins to degrade to the traditional multi-user MIMO network. The figure also shows that the average number of CSI feedback times in downlink is even smaller. It slightly increases while the number of AP's antenna increases, finally fluctuating around 1. The results shows that type has a great performance in reducing CSI feedback for both uplink and downlink multi-user MIMO transmission. Longer channel coherence time does not mean higher reusability of CSI, which is also influenced by distributed user selection and scheduling. To measure CSI utilization, we introduce packet length per CSI as the indicator to illustrate the average packet length decoded by different users' CSI in multi-user MIMO network. As shown in the figure above, present the packet length per CSI values for each user after 100 consecutive concurrent transmission in an 8-user multi-user MIMO network between 2 and 4 access point scenario. Since the 802.11ac has specified the maximum data packet length, the packet length per CSI of traditional network is not more than 5.5 milliseconds. In tab, all the packet lengths per CSI values of different users have been improved to varying degrees. Moreover, when faced with the same scale of users, the packet length per CSI values will increase significantly with the growing of access points antenna. Then is the channel detection overhead. The figure illustrates the average channel sounding overhead during each round of transmission under different user population. We conduct these experiments with 4 antenna access points. While the overhead in standard 802.11ac and Opus increases with the increase of total user number, the overhead in guidepost and type is almost constant. In a topology with 20 users, it achieves almost 7.5 times, 6.6 times, 1.5 times, and 4.5 times overhead decrease over 802.11ac, Opus, Guidepost, and RAW5 respectively. Obviously, tab outperforms all other schemes. We run a benchmark scheme with 20 users to validate the effort of number of AP's antenna on overhead, and plot the result in the figure above. It is clear that the overhead increases when the number of AP's antenna grows in all these 4 multi-user MIMO systems. However, the growth rate in type is still in a tolerable range. Hence, type can be scalable easily. For downlink multi-user MIMOs shown in the figure, standard 802.11ac, Opus, and Guidepost have almost identical throughput. Since there is no need of user selection, only concurrent users need to report their CSI. Ro-Fi saved the CSI feedback overhead by mobility awareness, which also work with a little higher throughput in mobile scenarios. Type achieved the highest throughput among all schemes. It's because that each concurrent users within channel coherence time can continuously receive data from access point without CSI feedback. Moreover, the performance of type in static scenario is better than it in mobile scenario due to longer channel coherence time. For uplink multi-user MIMO shown in the figure, Ro-Fi Opus, Guidepost, and Type have too much higher throughput than 802.11ac. In order to select the orthogonal users, access point needs all the users to report their CSI in 802.11ac. The four novel multi-user MIMO protocol have reduced much channel sounding overhead and user access time to different extent. Especially, Type utilize multi-user balanced scheduling method to provide higher CSI utilization and stable data transmission availability, so that the throughput of Type is 1.5 times of 802.11ac. Moreover, zero CSI cannot profile the channel state accurately, which degrades the efficiency of data transmission. Thereby, Ro-Fi and Type have consumed quite less energy than them based on the direct reduction of CSI feedback times. In addition, the fluctuation of energy consumption in Type is lower than all other schemes, benefiting from the comprehensive and balanced guarantee for the channel efficiency. And the conclusion we come to is that, firstly, demonstrates that the unnecessary CSI feedback from concurrent users will lower the throughput in multi-user MIMO network due to the high superfluous overhead. Secondly, by using the timeliness-aware balanced mechanism Type, unnecessary feedback overhead has been eliminated. The CSI utilization and channel throughput has been improved. Finally, extensive experiment results show that Type can substantially improve the throughput for multi-user MIMO network by 1.5 times least. That's it for the presentation. Thanks for your listening.
I'm so honored to be with you to communicate academic questions and ideas. The title of my paper presentation is Towards Mobility-Aware Dynamic Service Migration in Mobile Edge Computing. I come from China University of Petroleum, Beijing. The content is listed as follows: Introduction, User Mobility Model, Migration Model, Simulation Results, and Conclusion. In most of mobile edge computing scenarios, the devices and users on the edge side can only access to the services within the signal coverage of edge base stations or MEC service. However, the locations of users and devices are time-varied and dispersed in a wide area. When they move out, they have to reconnect to another MEC server or a cloud server, resulting in a service interruption. To address the issue brought by the user mobility, dynamic service migration techniques have been put forward for improving user experience under MEC. The basic idea of dynamic service migration in edge computing is to migrate the services from one edge server to another edge server according to the movements of the users being invoking the services. Figure E illustrates a typical scenario. In service migration, we have to solve the following two problems. The first one is whether or not to migrate a service at a certain time point. And if yes, the second one is where to migrate the service. Migrating a service may cause service interruption and bring in network overhead, whereas not migrating a service may increase the data transmission delay between the user and the edge server that hosts the service when the user moves away from its original location. It is quite challenging to make an optimal migration decision due to the uncertainty of user mobility as well as the complex trade-off between the costs related to migration and distant data transmission. To address this problem, this paper presents a mobility-aware dynamic service migration scheme for mobile edge computing. First, we propose the user mobility model. To solve the migration problem effectively and efficiently, we consider a time-slotted model for formulation. The user mobility and optimal places are obtained at the beginning of each time slot according to the state of the user. The length of the time gap interval is denoted by t, and the state of a user at time t is expressed as equation 1, where xt and yt are the coordinates of the user and vt is the velocity. Service migration is more likely to occur when users move near or across the cell boundaries. However, how to define the boundaries depends on the velocity of the user mobility. Therefore, as Figure 2, we dynamically define a target area TA according to the upper bound of the velocity, which is denoted by Vmax, and the width of a TA is given by equation 2. At each decision epoch, only the users in the TA are possible to move to another cell, which may trigger a service migration. All the users in the central area otherwise will remain in the cell during the time interval. Consequently, we need to calculate the possibility of a user to move to another cell only when the user is located in the TA. Then we use geometric knowledge to calculate the possibility of a user to move to another cell. Then we define cost model. When predicting that a user will move to the coverage of another edge server with a high probability, a reasonable decision should be made whether to migrate the service being used by the user to the other edge server. The objective is to balance the trade-off between the OSC degradation and migration cost. For both of them, the distance should be fully taken into account for analysis, while other factors, such as the size of the service, should also be considered. Let UT and WT denote the locations of the user and the service at time t. Respectively, we assumed that WPT is the location of the service that we try to migrate. According to the prediction result obtained from the mobility model, since communication cost, which is closely related to the distance between the user and the service, the communication cost is expressed as equation 13. The decision on triggering a service migration may bring in additional migration cost, and this type of cost depends on the distance between the locations of before and after the service migration, denoted by WT and WPT respectively. Moreover, the size of the service also has a certain impact on the cost of service transfer, since transferring a big service may consume considerable networking resources. Similar to the communication cost model, we define the migration cost using equation 14. Considering both the communication cost and the migration cost, the total cost of our model is given by equation 15. We formulated service migration by a Markov decision problem, and we selected policy iteration to solve Markov decision problem. The procedures of the policy iteration algorithm is shown in algorithm 1. Where CAS is determined by the communication cost and the service migration cost. The output is the service migration strategy pi in a certain state. That is, in the case of service migration, which service should be migrated from the current server to the surrounding server, which can minimize the total migration cost Vs. Then we use a real-life dataset containing the GPS trajectories of some taxis in the city of Beijing. In our experiments, each active taxi is regarded as a mobile user in MEC system. The relationship between the GPS track of the taxi and the cellular network is shown in Figure 4. Subfigure A is the display of the GPS track of the taxi in the map, and subfigure B is the display of the GPS track of the taxi in the cellular network. Among them, the center of the hexagon is the base station, and the size of each hexagon is the coverage area of the base station. We set the radius of the hexagon is about 400 meters. In order to validate the effectiveness of our approach, we select another 3 schemes for compression as follows. Non-migration is the service will not be migrated no matter how the user moves, unless the distance between them exceeds the maximum threshold. Always migration is we always migrate the service as well as the user moves to another cell. Random walk model is we still use the MDP algorithm to find the optimal solution, but replace our mobility model with a random walk model, which has been widely applied in service migration. We assume that the probability of the user leaving a cell is p, and thus the probability of staying inside the cell is 1/6p. We analyze the algorithm by changing the migration cost parameters, and the results are shown in Figure 5 and Figure 6. Then we analyze the impact of the maximum distance between the user and the service to maintain communication on the total cost. The result is shown in the Figure 7. The costs of the 4 migration strategies are compared by tracking the driver simulation, and the results are shown in Figure 8. The comparison results show that in almost all cases, The proposed method has lower cost than other methods, which makes our algorithm better verified in the migration decision. In this paper, we investigate the mobility-aware dynamic migration problem in mobile edge computing. We propose a geometry-based user mobility model for predicting the probability of a user to move out from the coverage of the current edge server to another one. Considering the trade-off between QoS and cost, the service migration is formulated by a Markov decision problem. An algorithm is designed for finding the long-term optimal solution. Finally, extensive simulations have been conducted to evaluate the effectiveness of the proposed algorithm, and the impacts of the model parameters are further analyzed. The experimental results show that our approach can dynamically find the optimal service migration decisions by reducing the cost while improving the QoS. This work is expected to provide a theoretical model and a practical solution of optimal service migration in MEC systems for mobile users. Thank you.
Hi, I'm Yuan Chuyin from Zhejiang University of Technology, and I will present our work, research on debugging interaction of Internet of Things devices based on visible light communication. This is a joint work with my colleagues, Jiefan Qiu, Changlin Li, and Minsheng Cao. Wireless sensor network nodes are often deployed in inaccessible environments, such as closed museum showcases. In such environments, it's difficult to connect and repair in a wired manner. In this case, wireless networks are usually used to update and repair these nodes. However, the failure of some nodes is often caused by a wireless network failure. How can we fix the lost sensor node with a wireless network failure? In existing method, the following method is usually used to solve this problem. In practical, developers have to abandon these lost nodes and replace them by backup nodes to which the tasks running on lost nodes are migrated. The problem is that developers rely on experience and intuition to determine whether the task should be migrated, and that is usually inaccurate. To this end, we hope to find an alternative debugging interaction method without modifying the local hardware of sensor nodes. In recent years, with the development of visible light technology, the general sensor node and the smartphone equipped with visible light components such as LED, camera, and ambient light sensor. These components provide a potential capacity for visible light communication. Visible light communication adopts unidirectional propagation different from the traditional radio wireless net communication with broadcast wave. This kind of propagation is not easy to be intercepted or eavesdropped and improve in transmission security. In addition, visible light communication does not occupy the bandwidth resource of current sensors networks and affect the wireless communication between sensor nodes. Therefore, we try to apply visible light communication in debugging interaction. In this paper, we implemented a hybrid duplexing debugging interaction system based on visible light communication applied in general sensor nodes. We tapped the potential capacity of visible light communication components in smartphone and sensor nodes, and regard the smartphone as the visible light communication-based gateway for debugging nodes. The debugging interaction uplink mainly transmits debugging information from the malfunction sensor node. It leverages the smartphone's optical camera as the signal receiver and the node's LED as the signal transmitter. The debugging interaction downlink mainly transmits updating codes to fixed nodes. It leverages the smartphone's flashlight as the signal transmitter and the sensor node's ambient light sensor as a signal receiver. Due to transmitting debugging binary code with downlink, two methods from source coding and channel coding are proposed to improve downlink transmitting performance. In source coding, we designed a compression method by analyzing instructions. An instruction includes operation code and operand. Instructions are divided into three types: single operand instructions, double operand instructions, and jump instructions. We have analyzed the instruction structure and removed some fixed operation code binary data and further compressing the operand. And instruction may occupy different number of bytes due to different addressing modes. If this is a multi-byte instruction, then its operation code and operands are in different bytes. The operands of multi-byte instructions will be further analyzed. Next, we will introduce compression methods for single byte instruction and multi-byte instructions. In single byte instruction compression, the encoding format as the picture shows. The operand is classified as other parts. The other parts which contain the part of the instruction except the operation code will be directly transmitted. Then we found that each type of instruction has a fixed fragment on the operation code. So the fixed fragment can be omitted and only changed fragment is transmitted. Therefore, the OP code in the format only contains the changed code. Because each type has a fixed fragment, we can use the sort flag indicate the types of instruction for restore fixed fragments during decoding. In multi-byte instruction, the compression method for the byte of operation code is same as single-byte instructions. For the operand part, we considered a method of replacing the or-zero sequence to compress the data. The pattern indicates different type of mask, and the group number indicates the position of the masks. The masks indicate the position of non-zero data replaced. Then the pattern 1 indicates that no mask can mapping the operand. When decoding, non-zero data will replace zeros corresponding to the mask in like the picture. After the first step of compressing the binary data, a better modulation method can be designed to further compress the code. However, the commercial off-the-shelf devices usually have low accuracy, making it difficult to achieve high-speed data transmission. Therefore, there is necessary to improve existing modulation methods to solve this problem. To this end, we've designed the ODH-PIM based on the existing DH-PIM modulation method. Before introducing the ODH-PIM, we want to introduce a new state used in ODH-PIM called LED half-on state. Using the ambient light sensor, the measuring process of light intensity needs a duration of light on state. If we intend to shorten the duration, the sensor captures a new LED state different from flashlight on and off state. We mark the new state as LED half-on state. A symbol of a DH-PIM usually contains 4 bits of data. However, the ODH-PIM can compress 8 bits of data into one symbol because 2 sets of data can be overlapped. and because different sets of data have a different time slot size. When two sets of data slots are overlapped together for modulation, and special plugs need to be used to separate them. At this time, the LED half-on state plays an important role. After representing the content of two sets of data, a time slot plus is introduced as an order flag. Indicates the order of the two sets of data. If the order flag is a LED half-on state, reverse the order of two sets of data. And a set of reverse flag is used to determine which set of data needs to be complemented. If there is a LED half-on state, then the corresponding data must be complemented. Based on the Android operating system and the general sensor node, we realized a hybrid duplexing optical communication system using a commercial off-the-shelf Android smartphone and a popular sensor node's telespeed. And we conduct a series of experiments about updating code blocks from 5 different functions. First, we report the overall performance of source coding and channel coding, respectively. In source coding, we compare the compressed code size with the original code size. It's obviously that the size of the code block is reduced as at least 8%. The compression method is available. In channel coding, we compare the ODH-PIM with DH-PIM. In the most cases of transmitting code blocks, our method is better than DH-PIM because ODH-PIM can effectively reduce the length of a symbol. The bit error rate is an important fact to evaluate performance of ODH-PIM. It's obviously that bit error rate is very high if the transmission distance is over 20 centimeters. The reason is that the sensor is difficult to detect the LED half-on state once exceeding 20 centimeters, and the bit error rate boosts due to lack of the state. When the angle is less than 25 degrees, the sensor is able to capture enough light intensity from the flashlight, so the visible light communication can work with a low bit error rate. Finally, we compare the energy consumption of the ODH-PIM and DH-PIM. We use ODH-PIM and DH-PIM to transmit the above 5 code blocks respectively. Since realizing the LED half-on state in ODH-PIM requires flashlight remain a duration of high-speed flash, it will pay extra 7.36% energy consumption than DH-PIM. The DH-PIM may consume more energy because it spends more time to transmit. That's all. Thanks for listening.
Hello everyone, this is a presentation of my paper. Its name is a Trojan attack on dialogue system of smartphone. I'm Deng Chang from USTC, and these are my team members. This is the context of the presentation. There are 5 parts of it. The first part is the background. The idea of the paper is inspired by a classic movie, 2001, The Space Odyssey. You must know it. It's a classic science film in 1968, which follows a voyage to Jupiter with a sentient computer HAL. This is the appearance of the HAL. It's just like an eye. In fact, it's an onboard AI of the spacecraft. It controls the whole system. It has advanced natural language knowledge. But the HAL is even smarter than human and has its own consciousness. In the end, HAL goes crazy and plans to murder the crew of the spacecraft. When Dave Bowman, the astronaut, asks HAL to open the pod bay door, but HAL has its own consciousness. It receives in response, "I'm sorry, Dave, I'm afraid I can't do that." It's a very classic dialogue in a science film history, and it shows a high level of the AI. In the end of the film, HAL goes crazy and murders the crew in the end. So it gives us a question: do AI systems safe? This is a robot controlled by an AI system. It brings us convenience, facilities, and applications. It's just like an angel. On the other hand, if the system is out of control, it can also threaten people, hurt people, even kill people, like HAL. Another question is, does HAL only exist in fiction or films? Unfortunately, the answer is no. Let's look at the accident of smart home in the last year. Danny is a young girl. She's a nurse. She has Alexa from Amazon. Danny wants to know something about heart disease, but Alexa answered, "Stab yourself in the heart for the great good." It's a very horrible accident. Fortunately, it only happens on a smart speaker. But what if such accidents happen on some critical devices? So it warns us safety should be concerned and smart home. Now, one more thing I want to mention that is current devices in smart home are not smart as hell, but they are vulnerable to be attacked. We design a Trojan scenario at smart home in this paper. This is a typical smart home. All the devices, furniture, and instruments are controlled by dialogue systems, just like Alexa. This is a Trojan scenario we designed in this paper. This is a user of smart home. These are the robots in it. The robot 2 is a normal robot, and it receives the information of the user and do what he wants. But robot 2 is a Trojan robot. It's a hacker. It receives the same information of the user, but it crafts adversarial example to attack robot 2. So the original information is classified as to positive, but The adversarial example is classified by robot 2 as negative. This is a normal dialogue system of smart home. A robot receives the wave of the speech of the user and put it into a speech signal processing system and transform it into a text. And the text is input to an NLP or NLU system to understand the meaning of the user. In this paper, only the part in this box is involved. The next part is preliminary. The first one is adversarial attack in text. Suppose that we have a DNN model. We divide f of x. Here we have an input, a text. We input it into the DNN model and get a result y. And we have another input, x prime, where x prime is similar with x. We input it into the same model, but we get another result. So the mathematical definition is f of x equals y, and f of x prime is not y, where x is similar with x prime. For salience, we have another model, and this is the input. LeBron James is a basketball player, and the classification result is false, and the confidence of it is 0.9. We want to know the importance of every word, so we replace the word one by one by unknown token and get the results respectively. So we have a distribution of every word to the result of sports. So the distribution is called word salience. We use the attention bioST model as our DNN model. This is a word-based layer, and this is a bioSTM layer. It processes data in both directions, and the edge concatenate is the final output of the hidden layer. In attention layer, the attention weight is the effect coefficient of xi, and it's refreshed by this formula. It represents the similarity of OI and edge concatenate. Here is OI, and here is edge concatenate. After that, this is the output layer. We set a full connection layer and softmax layer to get the final classification, class I. The next part is method. Our method is called attention probability estimation. This is a text which is composed of n words, omega 1 to omega n. We input it into a bioSTM model and get an output. Y is the label of class I. A is a distribution of attention weights. F is a function of the whole model. What we want is find a word omega I to be replaced to get a new text x prime. We put the x prime into the same model and get another output y prime. So the question is how to determine which word to be replaced. We use this attention weight distribution to determine the replace order. The word with the highest attention weight is the first candidate to be replaced. The attention weight explicitly reflects representation of input components, and this weight can be used to identify the importance of the input. So we can find the substitution candidates without computing the salience map. This is a word replacement strategy. First, we want to determine the replaced word by attention weight. In this text, the ith word has the highest attention weight, so we want to replace it. Then we get a synonymous set of omega I in wordlet. After that, we want to replace omega I by the synonymous and find a word which changes the output most. Then we get omega I star is the ith word substitution, which changes the output most. We can also select keywords to be replaced to strengthen the attacking effect. After keywords are replaced in this text, a new X star is crafted. The former method is not efficient enough because the model runs many times according to the number of synonyms. So we designed another search method, attention-based search. When a synonym set of a word is built, we connect this synonym word to a new text and put it into the attention BioSTM model. And we get a prediction YS. If YS equals Y, the original label, words with no attention weight is selected. If Y is not equals to Y, words with high attention is selected. We repeat this step for all the keywords and key replacement candidates are selected. The next part is experiment. Dataset and model. We use IMDb sentiment dataset. It is a binary sentiment classification dataset. It connects highly popular movie reviews from IMDb. And we use attention BioSTM model. The word embedding dimension is 200, and there are 128 units in BioSTM layer. The original accuracy of attention BioSTM is about 90%. This is a comparison experiment between attention weight and salience map replacement method. The first one is salience map distribution, and the second one is the distribution of attention weight. We can find that the two distributions are similar in some extent. The word with darker background color means it has a higher weight in these distributions. This is the result of the experiment. K is a hyperparameter, which controls the number of the words we want to replace. The accuracy of the original model is about 90%. We select 5 methods in our experiment. The first one is random. It means the replaced word in the text are selected randomly. PWWS is a formal method based on salience map. The words with the highest salience weight are selected. APE is our method. It means attention probability estimation. The selected words are determined by the attention distribution. GS is general search. ABS means attention-based search. We can find that when the value of k goes larger, the effect of APEGS performs better. The last part is conclusion. In this paper, we designed a possible scenario of adversarial attack in physical world and crafted adversarial examples in real time. We proposed a novel method to estimate the probability of a successful attack in text. We proposed an algorithm to search possible adversarial words in short time. This is a presentation of my paper. Thank you.
Hello, my name is George Broughton, and this talk is on boosting the performance of object detection CNNs with context-based anomaly detection. Modern computer vision and object detection algorithms have transformed robotics in recent years. Of particular interest is deep learning algorithms that are capable of segmenting images according to what they contain. These methods generally work by first proposing regions of interest in the image that are likely to contain an object. Often it's actually a neural network itself that is performing this task. Then, for each region, they run something akin to a whole image classifier. One of the problems with this, however, is that the context of each detection is often not taken into account in these pipelines. Often, the presence of an object in a scene, for example a computer mouse, means that the chances of you also seeing something like a computer keyboard is much higher. However, often these object co-detection probabilities, a rich source of information for understanding an image and a scene, is not taken into consideration. So, what we investigated was whether we could introduce this contextual information to boost the performance of object detection algorithms, and to provide higher level information for robots. For robots, this might be the understanding that although a certain object isn't currently visible, based on the context around it, it's very likely that this object is perhaps just out of sight of the robot's cameras, or is likely to be encountered in the near future. Alternatively, seeing an object that strongly doesn't fit the current scene might signify an object of interest that the robot should perhaps investigate further or report to a human operator. We looked at anomaly detection methods and found autoencoders to be quite effective. These have the additional benefit of being neural networks themselves, so can be trained and run together with existing deep learning pipelines. We designed our system to take the output of an object detector, that is, a vector of probabilities for each class, and that becomes the input vector for our network, seen here on the left. Then, this autoencoder is trained to recreate these vectors as its output on the right via a bottlenecked hidden layer. The thinking goes that commonly seen groups of objects, by nature of being commonly seen together, will be well learned by the network and it will recreate them very easily. If an object is rarely seen with another group of objects, for example an elephant with a computer mouse and a computer keyboard and perhaps a chair that are commonly seen together, because of the lack of seeing this whole group before, the network will struggle to recreate the elephant part in the vector. We can detect this and flag it as strange to the system. The opposite is also true, and we can detect objects that are often seen in a group, but in a particular image, for whatever reason, are missing. This could be, for example, an image where there is some food and a plate, and perhaps a knife, but maybe the fork is just out of shot of the camera. When we put the knife, the plate, and the food as a vector into the autoencoder, and it then tries to recreate the scene, what we find is because of its previous learning, it also generally recreates it with a fork as well. And we can recognize this discrepancy, the fact that it's normally seen with a fork, but in this example wasn't, and flag it to the system as an object that's perhaps close by. It's probably important to note at this point that when we say the autoencoder is able to recreate the vector, and the recreated vector has a fork present, in the output vector it's not binary 1 or 0 values. What we see is that the probability of there being a fork is elevated somewhat, and we can identify this slight elevation in the probabilities as perhaps indicating that the fork is normally present in such a group of objects, but for whatever reason isn't. We trained our autoencoder by taking the training image annotations from Microsoft's COCO dataset, the 2017 version. We took just the annotations themselves, not the actual images, and trained our network to recreate these. The vectors we used as inputs were 80 elements long, corresponding to the 80 classes present in the COCO dataset. Then, we set the value corresponding to a person to 1 if there were people in the scene, dog to 1 if there were any dogs in the scene, etc. If there were more than 1 people in the scene, we would still just set the input vector to a value of 1. It was just purely the presence of people rather than the number themselves. We set the value of everything else to be 0. We knew that the autoencoder had to have an input size of 80 and an output size of 80 as well in order to recreate the input. But we didn't know how big to make the hidden layer. So we trained many different models in order to investigate the optimum size for this. We knew that if we set the hidden layer to be too small, to use an extreme example, if it was just a single neuron, then this would be completely unable to recreate the input vector with any real accuracy at all. However, if we use too many neurons, it wouldn't be generalizing the input at all. It wouldn't be an autoencoder, for example, if you had 80 inputs, 80 hidden layer, 80 outputs. And this would probably lead to quite severe overfitting of the training set. This graph is interesting because it shows the effect of removing a single neuron, the effect that it has on the loss of the model. So, for example, we can see on the right-hand side that at around 35 neurons in the hidden layer, if you remove a single neuron, then the effect on the loss is next to nothing. And this makes sense because 35 is quite a lot to recreate the input layer. However, when we get to 5 neurons, for example, if you remove one, then it creates a huge impact on the loss because the model is already really struggling to recreate the input vector. You can see that there's a sweet spot around 15 neurons, which is where the loss really starts to increase for each neuron that you take away. And therefore we elected to have a hidden size of 15 neurons. We performed a series of experiments to then evaluate the performance of this autoencoder and how well it could spot anomalies in image annotations. In experiment 1, we took the evaluation set from COCO, and for each image, we took the annotated objects and introduced an additional object which wasn't in the original image, and identified how well it could identify this extra object that we'd added. We also did this in reverse as well, and we took images where there were more than 3 objects in the scene, and we removed one from the scene, and we looked at how likely the autoencoder was to suggest that this object that we'd removed should somehow be present in the original image. For the second experiment, we combined the autoencoder with the YOLO, You Only Look Once object detector. And what we did is we examined how well the autoencoder could improve YOLO. And this comes about because if you have several objects in a scene, if we go back to our computer mouse and computer keyboard example, if you have a mouse present and the YOLO suggests that there is a keyboard there, but the probability is perhaps 0.49, and the threshold for the detector is 0.5. On the YOLO detector alone, this would be rejected. However, if it also makes strong contextual sense, then we can introduce a variable threshold and say if it fits the current scene, then we will perhaps let a 0.49 probability object pass. So again, for each image, we take the annotations, for example, mouse, keyboard, desk, chair, and we'll randomly remove one and see how well it can suggest that this object is normally present. And we'll also introduce an anomaly, for example, say there's a zebra there, and we'll see how well our autoencoder can suggest that this object is anomalous from the group. In these graphs, the axes on the left represents the accuracy, and the axes on the bottom represent the number of neurons. And if we take the negative anomalies, which is where we remove something, we can see that at, for example, 12 neurons, the model is able to identify objects that should be present about 20% of the time. And while this might seem quite low, if you imagine a kitchen scene, and if a knife and fork are not present, if you take them away, then this actually doesn't create an anomalous scene, because a kitchen without a knife and fork is still reasonable, because they might be out of sight, they might be perhaps tidied away. So 20% of the time being able to say that there is an anomalous object missing from this scene, and it's this particular object, actually seems reasonable. And furthermore, for a lot of images in the COCO dataset, they really only have generally 2, 3, 4, maybe 5 objects present. So when you remove one of these, you can really impact quite strongly on the contextual information of the image. On the right, we've got the positive anomalies, and we can see that, for example, at 10 neurons, if we introduce a new object which wasn't in the original image, about 80% of the time we can identify that this object doesn't really make sense somehow. And with many, many more neurons, 20, 25, we're hitting about 50% accuracy. It's important to note, however, that this is the accuracy of the anomalies, and that while 10 neurons might seem very good here, actually, as we saw before, 10 neurons had quite a high model loss. So when we balance this together, we find a sweet spot of between about 15 to 20 neurons. So again, for experiment 2, what we did was we had the images coming in from the evaluation dataset on COCO, and we fed it into You Only Look Once YOLO version 3. And then we took the outputs of this and split it into 2, and we fed one of those into our anomaly detection, and we took the outputs of the autoencoder and compared it back to the original outputs of YOLO, and then we could identify that our autoencoder was strongly saying that something is not present or is somehow strange in this scene. Then we could use this information to take the YOLO output probabilities and adjust them based on the contextual information. So going back to what we said before, if something is very strongly implied from the contextual information, if it comes out with a probability of 0.49 and just misses the threshold for what's classed as a detection from YOLO, if the contextual information backs this up as well, we will just let it pass. We can see the results of this here, and we have the threshold at the bottom, and on the left we've got the accuracy of the detector. So what we said was anything above 0.5 was a strong detection in the original YOLO detector, and therefore it doesn't make sense to use contextual information to interfere with this. It's already such a strong detection. However, between 0.25 and 0.5, this is the region that we concentrated on, these detections that fell in this threshold. And we looked at, we applied the previous model and said if it was strongly implied from the context and also made sense, then we included it as a detection. And as you can see, the actual accuracy of the YOLO is boosted when doing this, and we can gain up to about 4% accuracy just by applying this. And if we consider the impact of this, the millions of neurons present in the image detectors, simply adding a few hundred to the end of the detector to take into account context to gain several digits of accuracy improvement seems like quite a good trade-off. So just to show the results of this very quickly, the actual outputs of the autoencoder. In this first image, we've got a kitchen scene, and on the right-hand side of the image, there is actually a surfboard on the wall. And this is obviously something our network flagged as being quite strange, given the rest of the objects detected. In this next image, we've got a living room scene with chairs and tables, vase, this sort of thing present, and YOLO detected a horse present. And when we originally read this, we thought, yeah, this is quite strange, and loaded up the original image, and sure enough, there was actually a horse present in the form of a painting on the wall, but it is certainly somehow anomalous. And finally, in this image, what we found was this image had been annotated as having a person, a table, plate, food, cups, this sort of thing. And there was actually a sofa had been annotated because of this restaurant's layout. And our network suggested that there should actually be some chairs present, obviously not understanding the relationship between chairs and sofas. So given how lightweight this approach is compared to deep learning object detectors, we certainly believe that this approach is useful for robots in terms of boosting the object detector accuracy, and also for flagging objects to the robot that are anomalous or strange somehow and perhaps it should investigate, or perhaps that it's likely to encounter in the near future. Thank you.
Thank you, Ms. Chow, for giving us a chance to make a presentation on this stage. To begin with, please allow me to introduce myself. My name is Song Kai-yu, the reporter of this presentation, from School of Information Science and Engineering in Yunnan University. Today, it is my honor to share with you some of my research process on an efficient approach for parent interlearning of a Bayesian network with multiple latent variables using neural network and PEM. My presentation is structured in the following way. First, we would like to concrete the problem that we face in research of Bayesian network. Then, we are to show a contribution on the above problems. Third, the experimental result will be listed to prove our contributions. Finally, our presentation will end up with the conclusion for our contributions. Let's go to the first part, the problem. Nowadays, unprecedented amount of user behavior data can be collected and analyzed to facilitate the development of more realistic applications in economic and medical systems. An example is listed in the above figure. A user rates the movie Titanic with a 5-star rating as she or he prefers English movies and love stories. Specifically, 75 of females may consider the genre first, and out of them, 88 of the users may prefer love stories. As is seen in this example, multidimensional user preferences are often unobservable. Furthermore, various associations with uncertainty exist among user properties. The attribute of the movie, the observed rating, as well as other latent preference on various other aspects of the movie. Therefore, this task has 3 attributes: multidimensional preference, unobserved latent variables, independent relationships with uncertainties. To enable the analysis of their problems, it is desirable to construct a human-like model to achieve interpretable inference. This is why we use Bayesian network with multiple latent variables, abbreviated as BMML. Multidimensional preference and unobserved latent variables has been concreted by the multiple latent variables. The dependent relationships has been concreted by the percentage in CPTs. For example, for a user, we have 19% to choose the movie that the language is Chinese. Meanwhile, we can concrete the unobserved variables such as the vacation or the node, add the independent relationships, and build CPTs. By this way, we can build the model to analyze this task. However, multiple latent variables cause some troubles for learning process of BMML. It increases the number of combinations and further increases the number of parameters, which causes that it is difficult to learn BMML. How difficulty? The complexity of parameter learning, a part of the learning process in BMML, is shown here, where the variable p and s are the number of iterations and that of latent variables, respectively. The constant c is greater than 1, related to the number of parameters. As a result, original learning method is ineffective due to this complex function. Focus on this, we propose 2 methods. The neural network-based method, mixture of generate adversarial neural network, combining with RNN, abbreviated as RMGN, to reduce variable c. RMGN can be used to decrease the number of combinations by achieving clustering. This can achieve decreasing the number of parameters. Second, the PEM-based method. We use parabolic acceleration of EM algorithm to refine the original EM-based parameter learning and reduce variable p. So, let's go to the RMGN part. In this part, we will start with an overview of RMGN shown in the left figures. Our work in RMGN can be summarized as 4 parts: input, RNN layer, outputs, and the way to finish clustering, and replacing by using outputs. It should be noticed that RNN layer and replacing are the most important part in RMGN. The structure of inputs is shown as the right finger, which is composed by three components: choosing variables, DAG of choosing variables, and dataset. Normally, we can choose some observed variables as choosing variables. The DAG of these observed variables can be easily generated according to the dataset. Then, we turn to the RNN layer part. The main container in our layer is composed by StateGate and the recurrent mechanism. We create a new component called StateGate and insert it between our cells, shown in this figure. The DAG will be sent to the StateGate. We use it to incorporate the structural information of DAG into recurrent mechanism so that RNN can use independent relationships to help us achieve clustering. The recurrent mechanism is changed into a following function. We give the overview of the structure of a proposed RNN layer. The input x1, x2, x3 will be sent to corresponding cell R1, R2, R3. The recurrent values is not only from the previous cell. StateGate will use independent relationships to extend the sent values. We can see that the original passed value W1 from R1 has been changed to S1 by StateGate. To help us easily understand how it works, we give an example. First, we generate three cells to build one by one corresponding for three choosing variables x1, x2, x3. The DAG among three variables can be saved as the adjacent matrix GMM. We can use RNCL to generate Y matrix to save the result of three of these cells. Then, doing the recurrent mechanism shown in the right part here, we do the operation of inner product, which is dot product in example between GMM matrix and Y matrix. Here, you can see that after finishing the inner product, the information of the DAG is used in recurrent mechanism and can be sent to the next cell correctly, because if there is no relationship between the next cell and the other cells, the result of the inner product is 0. If there is a relationship, the result of the inner product will add the values from cells that have the relationship with the next cells. In this example, we can see that the next cell is x2, and the x1 and the x3 have relationships with x2. So the result of the inner product is the values of the x1, y1, and the x3, y3. Same operation will be done in the right part here. We can see that the next cell is x3, and the result of the inner product is x1, y1, and the y1 and the x1 has a relationship with x3. By this way, we achieve the fusion between BNMM and the neural network, and we successfully use the information of the DAG from the DAG to achieve the clustering. Now, we go to the next part, the clustering part. In this part, we will introduce how we use the result of RMGN to achieve what we want. After finished training, we can get the classes and the probability distribution for each class. We use class to generate labels for all symbols in dataset and generate new values for each symbol by using probability distributions. In the end, the new values are used to replace the original values for each symbol. The example of this process is shown here. We assume that there are two observed variables, gender and location. The independent relationship between two variables is also shown in this figure. After finish clustering by RMGN, we can generate the label for each symbol in dataset. Then we use new value generated by RMGN to replace the old ones and generate new dataset. By this way, we achieved reducing the number of combinations in choosing variables, and we successfully choose that we use a part of the BML into the neural network. Well, the next part is PEM. In this part, we will introduce the PEM and show how we use PEM to further improve the parameter learning of BML. We incorporate PEM to improve the original EM-based parameter learning method. In the parameter learning, SEM algorithm will provide a complete DAG and extending dataset to enable us to learn the parameter of CPTs. Therefore, we use this as the inputs and give the values for the constant in PEM to generate the seed P. To simplify the calculating operation, we generate a vector to save all seed generated from all parameters. Here we can see in the right part. If we have 3 parameters that need to be updated, we generate 9 seeds according to the PEM to build a vector. The column of the vector means 3 seeds for 1 parameter. After generating the seed, we can use the vector to calculate the parameter by using the values of each column based on PEM showing this. Finally, we check whether the new parameter P_new are satisfied with the terminating condition. If it is satisfied the terminating condition, we update these parameters. The rest will be set as a new seed. After finishing updating, we can get complete CPTs. To make us more easy to understand, here we give a complete process. Let's first look at it. The algorithm starts with the input of DAG and the constant. Then each step in SEM will extend dataset and send it to the PEM-based parameter learning part. We use this to generate seeds for each parameter that need to be updated and use all seeds to generate vector. Then, as what I have said before, we use vector to update parameter learning and check the terminating condition. If it's satisfied, we end the algorithm. If not satisfied the terminating condition, it will be used as a new seed as a P0 to generate P1 and P2 and build the vector again. To sum up, the main contribution in PEM part is that we use a function in PEM to refine the original EM-based parameter learning. The rest part is the experimental part. In this part, we will show the experimental result. We make 3 groups of the experiment based on our MU-MIMO and the cardiovascular dataset. The ARM dataset is used to demonstrate the effectiveness for reducing the number of iterations. MU-MIMO and cardiovascular is used to demonstrate the improvement and the validity of our proposed method. The result in ARM is shown in the below. Here, we compare the executing time of the parameter learning using different methods. The comparison was made for different sizes of ARM dataset and a different number of Latent variables. It can be seen that PEM and RMGN both works well, and successfully decrease the time consuming of parameter learning. In addition, PEM with RMGN achieves the best performance, since the average time consuming are the least. Next, the experiment results of MU-MIMO and the cardiovascular dataset shown as follows. We compared RMSE, MSE, MAE by different modules on different sizes of the dataset on MU-MIMO. The RSE, MSE, and MAE based on BML using PEM to finish parameter learning are the same as those based on BML using EM on MU-MIMO dataset, which shows that PEM achieves the same optimal values as the EM, This proves that PEM is correct. It can be seen that PM combined with RMGN gets the best performance in 3 metrics since the average of RMSE, MSE, and MAE are the least in Mueller dataset. To further illustrate the feasibility of BMML, we compare the RMSE, MSE, and MAE based on different models on different sizes of cardiovascular dataset. The model include BMML use different methods to fulfill parameter learning and a product neural network, in which the method of parameter learning of a BMML are the same as the experiment on movie lens. It can be seen that the performance of a BMML use PEM and RMGN is on average improved in terms of 3 metrics compared with the product neural network and compared with the matrix factorizations. This suggests that BMML is also feasible in cardiovascular dataset, and our proposed method is feasible. Finally, let's make a quick conclusion for our work. First, we propose RMGN to make an fusion between BMML and neural network by proposing state gate to rebuild recurrent mechanism. This is our main contribution in this work. RMGN can achieve decreasing the number of combinations and further decrease the number of parameter learnings by incorporating the DECS of BMML into clustering. Moreover, we incorporate PM into SEM to improve the parameter learning. Our work has been proven by the experiment that proposed method is correct and feasible. In addition, proposed method can achieve improving parameter learning. This is a main reference in our work. The details of some algorithms that has been referred above, such as SEM, product neural network, can be found in this reference. I hope you have found this useful. If there are any questions, please contact us by email. Thank you for your attention. This is all the content in our work.
Hi, this is Arash. In this video, I will present our paper titled as Cooperative Pollution Source Exploration and Cleanup with a Bio-Inspired Swarm Robot Aggregation. This video consists of 4 parts. The first part is Swarm Robotics and Exploration, which is an introduction to our work. In this part, the motivation for our proposed method is described, and also its background is given. Next, the decontamination method is described with its state machine and equation which rule the method. In the following sections, experiments and their results are presented. Swarm robotics is a new concept of multi-robot systems, and its primary goal is to solve the problems with the help of multiple simple robots. In extreme environments, such as relatively recent Fukushima disaster, most of the standard robotic functions fail to operate reliably in the presence of chemical and radiation contamination. Consequently, such environments require a fault-tolerant and robust robotic setup. The advantage of using multiple simple robots rather than a single complex one is multi-robot systems' ability to perform collective decision-making. This kind of collaboration among robots is very beneficial in extreme environments because it does not rely on only one robot's decision. So if a robot fails to act correctly, the overall decision will not be affected. Therefore, decisions made by swarm robots are more reliable and robust to possible malfunctioning robots. Our goal is to carry out the decontamination task with swarm of simple robots. Our method is mainly inspired by B-class method, which is a queue-based aggregation behavior of robots. Aggregation is a behavior that is observed in many different animals and insects like honeybees. Aggregation is the gathering of swarm members to a single group. This gathering gives swarm members new abilities like building a habitat, deterring much stronger predators, and defeating larger prey. Aggregation is observed in 2 types, queue-based and self-organized aggregation. In queue-based aggregation, robots aggregate by the help of external guidance called queue. For instance, bees aggregate in a zone with a desired temperature. On the other hand, self-organized aggregation is formed regardless of environmental properties and without any external guidance. B-class method is one of the most popular bio-inspired queue-based aggregation principles. By performing a detailed analysis of honeybees, which aggregate around the zone with optimal temperature, this method was proposed as a behavior protocol for swarm robots. The B-class aggregation method was chosen as a basis to implement our exploration method. This figure demonstrates the state machine of the B-class method. When experiment starts, robots start to move forward. When they encounter an obstacle, they turn randomly and avoid the obstacle. If they encounter another robot, they will wait for an amount of time depending on the temperature of the point where the collision has happened. When the waiting time is over, they will turn randomly and continue their exploration. These sets of simple rules result in aggregation of robots inside the queue. In this figure, we see the state machine of the proposed decontamination method. When the experiment starts, robots start to explore the environment. When a robot detects a queue, it tries to reach the center of it. In our work, queue represents the contaminated area. If a robot encounters a wall, it will turn randomly and continue its exploration. But if it meets another robot, it will stop and wait for WS seconds and clean the queue meanwhile. Waiting time WS depends on the intensity of the queue where robots collided. The more intense the queue is, the longer the robots wait and the more they clean. In original B-class method, robots do not clean the queue and do not move towards the queue center. The decontamination method consists of two parts, pheromone trailing and cleanup. Pheromone trailing is basically robots trying to reach the center of the queue. It is defined by two equations. NL and NR are speed of left and right wheels, respectively. Beta is the biasing velocity of motors. SR and SL are right and left sensor values. Alpha is the parameter to adjust the sensitivity of the motors to sensor readings. Higher alpha means robots will not react to sensor readings. In contrast, lower alpha will cause robots to overreact to sensor values, and it will result in robots' motion oscillation. Cleaning the contaminated part is achieved by the second equation. Sn is the queue intensity after cleaning. Sc is the average sensor value. P and Q are variables in the range of -4 to 4. The purpose of these two variables is to give a gradient decrease shape to the cleaned area. In this picture, you can see the real monorobot and its simulated version, which is designed in VBOT simulation software. We use the VBOT software to experiment our proposed method. In these three pictures, we can see Q's evolution during 4,000 seconds with 30 robots. At the beginning of experiment, the shape of Q, or the contaminated area, can be seen. In the next picture, we can see that robots start to clean the Q from inner parts which had more Q intensity and thus longer waiting time. And in the last picture, we can see that contamination has almost vanished. This figure illustrates mean Q intensity versus time for different populations and robot velocities. Shades represent the first and third quartiles, and the line itself is the median of results. As it is apparent, higher robot population showed better performance in cleaning the contamination. This is because higher population size results in better aggregation. In addition, by comparing the left and right figures, we can see that robots with higher speed could achieve better performance in all populations since they explore the arena faster and the chances of collision increase. This figure illustrates median coherency measured in meters versus time for three populations. As previous figure, shades represent the first and third quartiles, and the line itself is the median of results. The similar point of test cases is that they verge to a steady state after a while. On the other hand, they differ in the slope of verging to this value, as for higher population sizes, coherency reaches its steady state faster. When the steady state is reached, it means that Q is almost cleaned and the cooperation among robots are not considerable. This figure demonstrates the ratio of robots within a distance of 0.7 meters from the source of contamination. It merely represents how close robots were to the center of the queue. As population size increases, this metric's performance reduces since contamination is cleaned faster and there is no queue left to attract robots to its center. In this table, we can see the results of ANOVA test for the outcomes of experiments. ANOVA stands for Analysis of Variables. Thanks for watching.
Hello everyone. I'm Fu Xiaozhou from Shanghai Jiaotong University, Shanghai, China. Today, I'm going to give a presentation of my paper, DECS, Collaborative Edge-to-Edge Data Storage Service for Edge Computing. First of all, I will introduce the research backgrounds of this paper. Nowadays, the amount of data is becoming larger and larger, and the performance of hardware is also becoming more and more powerful. There are three principal goals of this paper. The first one is to utilize the resource of edge nodes in small-scaled scenarios effectively. The second one is to lower the reader latency. And the third one is to decrease the cost of the whole edge cluster. Existing solutions such as traditional cloud computing, classical wide-range edge computing, or distributed database. However, they were not suitable for small-scale edge computing scenarios because the existing solutions are not lightweight enough and didn't take the limited storage resource of edge nodes and the heterogeneity of the edge node into account. The contribution of this paper mainly consists of 2 points. The first one is to abstract the storage as a service and propose DECS. And the second one is to design, implement, and evaluate DECS. The DECS proposed in this paper is suitable for small-scale scenarios such as a college campus, a parking lot, a hospital, an industrial park, and so on. The figure on the left shows the scenarios of classical edge computing, such as metropolis computing, smart city, and inter-metropolis computing. The figure on the right shows the scenarios of small-scale edge computing. The figure shows an example of an office building. DECS abstracts storage as a service and runs on the edge node as a service. The right figure shows the overall framework of the DECS. DECS consists of metadata module, data storage module, data processing module, trade-off module, and a prediction module. Firstly, I will introduce the metadata module of DECS. The metadata module records 4 types of metadata, which are data's meta information, data's access records, edge nodes merchant status information, and the whole edge cluster's information. Metadata is stored as key value pairs and organized as JSON strings. The metadata module of each node in the cluster communicates with each other through the gossip protocol. And the right figure shows part of the definition and the pattern of metadata. There are 2 types of operations in the data storage module, which are the write operation and the read operation. The purpose of the write operation is to write the data to the place where the data is mostly likely to be consumed. By default, the data will be written to the closer edge node. However, the data storage module will check whether there are forwarding rules for the end devices firstly. If so, it will store the data according to the forwarding rules. If not, this module will pick the most appropriate edge node to write data according to the disk, bandwidth, or load balance of the edge nodes in the cluster. By default, the read operation is read from the closer edge node. If there is no required data on the nearest edge node, the read operation will be forwarded. If there are multiple copies of the data in the cluster, the data storage module will pick the most appropriate edge node to read the data according to the disk, bandwidth, or load balance. In this paper, the data can be divided into two types. One is temporary data, which is usually generated by ROT devices and mostly used for real-time computing. And the other type of data is regular data, which is usually generated by mobile phones or laptops held by users, and the principal purpose is to persistence. This algorithm shows the process of the write operation. When writing data, the data storage module will check whether there are forwarding rules for the end device firstly. If so, it will get the target edge node according to the forwarding rule. If not, it will pick the most appropriate edge node from the cluster to write data. And this algorithm shows the process of the read operation. When reading data, the data storage module will check whether there is a data in this edge node firstly. If not, it will query which edge nodes have the required data by the metadata module and pick the most appropriate node to read. The data processing module is to solve the data storage problems before and after the task is offloaded to the edge node. The data processing module is supported by the data storage module. In this paper, the tasks are divided into two categories. One is with data tasks, and the other is without data tasks. The differences between the two tasks are shown in the table below. And this algorithm shows the process of processing with data tasks. Firstly, the data storage module will return the nodes in the S cluster that can store temporary data, and then the trade-off module will pick the most appropriate node to execute the task according to the idle CPU power. The trade-off module provides formulas to pick the most appropriate edge nodes to write data, read data, or process offloaded tasks. The highest score node is picked as the most appropriate node in the cluster. As shown in the formulas, the free disk space, the predicted access amount in the next period, and the transferring time are all taken into account. The prediction module can build forwarding rules for popular end devices and also can distribute popular data to other nodes. Forwarding rules can directly store the data to the edge node in which the data is most likely to be consumed. There are two kinds of distribution strategies in this paper. One is to replicate and distribute the popular data, and the other is to continue to forward the read request of the popular data without replication. The prediction module uses the LSTM model to predict the access amount in the next period. In this paper, DECS is implemented by the Spring Cloud framework, and the edge nodes are simulated by Docker containers. Because of the difference in performance between edge nodes, this paper limited the performance of Docker containers and divides edge nodes into three categories according to their performance. The end devices are IoT devices and mobile phones or laptops held by users. The detailed experimental parameters are shown in the table below. This paper uses two small-scale scenarios to evaluate DECS. One of them is the path-fitting application. The data in this scenario is temporary data and generated by IoT devices. The other is the edge Dropbox application. The data in this scenario is regular data and generated by mobile phones and laptops. The experiment's results are compared with two baselines in this paper. One is a simple service that only provides the read and write interface without other data strategies, and the other is LF store. The evaluation of performance is mainly to the storage module, prediction module, and trade-off module of DECS. The evaluation indexes are the latency of read operation and the standard deviation of resource utilization distribution of edge nodes. This paper evaluated the storage module and the prediction module firstly, and the first figure evaluates the ratio of forwarded requests and read latency before and after building forwarding rules. The second figure shows the evaluation of read latency before and after replica distribution. The experimental results show that the forwarding rules forwarded by the prediction module and the replica's distribution strategy can lower the reader latency. And then, this paper evaluated the trade-off module. These two heat maps show the free disk utilization and average idle CPU utilization of the edge cluster during the experiment. And this paper calculates the standard deviation of the cluster resource utilization. The experimental results show that DECS fully considers the uneven performance distribution of edge nodes, and the trade-off module can make the resource utilization more uniform and improve the resource utilization of the edge nodes and edge cluster. Well, okay, the above is my presentation. Thanks for listening. If you need more detailed content, you can read my paper. And if you are interested in this research, you can contact me. Thanks.
Ladies and gentlemen, thank you for finding the time to come and join me for this presentation. Today's topic is a deep collaborative filtering approach based on content text fields for recommender systems. I'm going to explain this topic in 4 aspects. First, I'll go through introduction and motivation. Next, I'll state the model we addressed it. Then, review the related experience we had done. Finally, I outline the conclusions, and after that, there'll be the time for questions and discussion. Now, let's start with the first part, introduction and motivation. As we all know, recommender systems are an effective way to solve the problem of information overload. It can find the valuable information to meet the user's maximized demands quickly and efficiently. In other words, it provides unique user with a personalized recommendation service. And nowadays, recommender systems are almost everywhere. For example, when you watch a video, you will find the video recommendation. When you search for a product, you may find the advertising recommendation. So, as you can see, the recommender systems have been adopted in the numerous fields, such as information retrieval, e-commerce, and so on. As for the methodologies of recommender systems, its measures include the collaborative filtering, content-based, and hybrid strategies. The collaborative filtering is the most widely applied among these models. It uses the similarities among items to recommend for users. However, the existing traditional recommendation methods suffer from some issues. The first one is that only one of implicit or explicit data was used to infer the latent factors of users and items, whereas both implicit and explicit feedback are equally important. And take both of these 2 kinds of feedback information into consideration is necessary too. The second one is only the rating data is used to learn the representations, whereas the ordinary information is ignored. As we all know, the growing of the number of staffs and users in applications will sharpen the sparseness of rating data, which will have a bad impact on the performance of recommendation. The last one is, although some traditional methods employ the content text as ordinary information, but they only use deep neural networks to deal with the rating data. As for the content text, they just utilize the bag-of-words model to learn, which has some limitation in learning the semantic features and deep latent features. To address these issues, we propose our own model. We know that user representations of rebating base is benefit for learning the latent text features, owing to where rebating can be pre-treated on large corps through an unsupervised way. In addition, using the neural networks can better understand the deep latent feature vectors of text as well. So, turning to the methods, the finger on the right side shows the overall framework of our model. It leverages both of interaction data and ordinary information to make recommender predictions through 2 parallel neural networks. On the left part of this finger, we obtain the deep latent feature representation of items and users from the rating matrix by using the multi-layer neural network. And we can get a vector of item Q and a vector of user P. Meanwhile, on the right side of the finger, we convert the content text into latent future vector through embedding layers and neural network layers. And we can get a vector of item T as well. Then we adopt the linear strategies to fuse the two kinds of item vectors, which was extracted from two kinds of data, to get the final item representation. And we use this item representation and user representation to make a prediction. In the details of our model, the first is how to construct the interaction matrix Y. Generally, some recommendation methods employ the equation 1 to construct the interaction matrix. But this equation only regards the observer ratings as value 1 if user had an interaction with item, which will ignore the significance of the user's preferences, while the equation 2 reserves the value of ratings. It can be inferred as a numerical value, and which is on a scale of 1 to 5. So the equation 2 can be applied to show the degree of preferences of user on items. And based on this, in our work, we employ the equation 2 to construct the interaction matrix Y. In the meanwhile, we mark 0 if ratings of users on items are unknown, which can be taken as the implicit feedback. In our model, we extend the latent factor model to predict the ratings, where the vector P refers to the latent future vector of users, and the HX indicates the final item representation. It can be referred as an item's universal future extractor. But how to construct it? In our work, we use the linear strategies to fuse the two kinds of item future vectors to model it. One is Q. It was an item vector learned from the rating matrix. Another is T. It's still an item vector, but learned from the content text. For getting a better result, both of these two item vectors have been processed by the neural networks. As for the loss function, we utilize this equation of new normalized cross-entropy loss as our objective function, for it can do well with the implicit and explicit feedback data. Well, this is all the details of our model, and in order to verify that our model is very effective, we did related experiments to prove it. Going to our experience. In our work, we use 3 kinds of datasets, and this table shows the character of these datasets. The data of Amazon covers the comments of items, which can be deemed as the content text. However, the movie lens does not have the description of items. So we capture the content text related to the items from the IMDb. In addition, we utilize a matrix of normalized discounted cumulative gain, called NDCG, and hit ratio, which called HR, to make evaluations on the models. So in the experience, we compare the model with other 5 methodologies. It is BPR, CRT, neural metric factorization, convolutional metric factorization, and deep metric factorization. And the experimental results are shown in this table. From it, we can see that our model outperforms than other methodologies. In details, Compared with the model of DMF and neurometric factorization, by the way, these two models do not exploit ordinary data. And compared with it, DCT is more expressive, and the result can be proved that adding the ordinary information into the model seems very useful for promoting the performance. As for the model of convolutional metric factorization, which adopts the review document, but do not consider the deep latent feature of user and item in interaction rating data. And compared with it, our model still has a better performance, which could be proved that using the deep neural networks to process the content text vector could improve the performance of recommendation. In the meanwhile, we had done the experiments of sensitivity to hyperparameters. This table indicates the performance variance with disparate value of integrating ratio alpha. The result shows that the value of alpha around 0.2 and 0.8 to achieve the best performance. It can be proved that integrate the representation of content text into the model and utilize two parallel neural networks to learn the latent vectors from the ratings and content text at the same time seems very useful. Also, we had done the related experiments on hyperparameters of depth of neural network layers. Those figures study the impact on the performance with different layers on each iteration. It can be proved that the deep neural networks seems to be a little helpful for promoting the performance. As for the hyperparameter of negative sampling ratio, this table indicates the performance variance with different sampling ratio. From it, we can see the negative instances value around 5 can get an optimal performance on 3 datasets. Besides, the experimental result expresses that the more negative instances, the better performance of the model would be. And last, we had done the experiments on hyperparameter of final latent space factors. This table shows the performance with number of disparate factors on a scale of 8 to 128. From it, we can see the representations with more factors can be more effective in prediction. All in all of this experience have proved that our model is very effective and can improve the performance of recommendation. Well, let's move on to the conclusions. In this paper, we proposed a model DCT which will use two parallel neural networks to deal with the latent vectors, which was extracted from the data of ratings and data of content text. In the meanwhile, this model is proved to be very valued and achieves a dramatically improvement performance in recommendation according to a lot of experience. As for the future work, we would like to adjust other ordinary information into the model of DCT and explore some complex models on dealing with the content text, which can better understand the semantic features and deep latent features of text. Now, that's it all. Thank you, everyone. I hope I have addressed the major concerns about this issue. And thank you, ladies and gentlemen, for your kind attention. Thanks.
Hello everyone, I'm glad to be here to show my work. I'm Li Jiawei. The work I'm going to show is related to real-time self-defense approach based on customized Netlink connection for the industrial link-based devices. I will introduce this paper in 4 parts. First part is about overview. With the deep integration of information technology and operational technology, various Linux operating systems have been successfully applied in critical industrial devices, such as Linux-based industrial Internet of Things, controllers, or gateways. And the vulnerability of these systems may become a new breakthrough for the organized and high-intensity attacks. In order to prevent malware from corrupting or disabling industrial Linux-based devices, this paper proposes a novel real-time self-defense approach which can be easily developed without resigning the basic software and hardware platform. In recent years, the development of information-enabled industry has promoted a large-scale integration and interconnection of current industrial control systems, and the original self-imposed isolation of various industrial components has been broken. As a result, the threat of increasing vulnerabilities appears as a non-linear superposition, and today's industrial control systems are suffering from serious security threats due to the organized and high-intensity attacks. Especially advanced persistent threats has become the most popular and dangerous attack pattern, which infiltrates and destroy industrial infrastructures by exploiting various hidden zero-day vulnerabilities. In order to achieve the deeper integration of information technology and operational technology, various Linux operating systems have been widely applied in critical industrial devices. For example, an open-source industrial IoT gateway is designed by exploiting the microservices of Docker, whose software solutions are mainly based on Linux, and a software CNC controller which runs the Linux real-time operating system is developed to implement the EPL DECS as a real-time kernel module. As a result, the vulnerabilities of Linux operating system become a subject worthy of special attention, and some potential security threats which aim at damaging and affecting the Linux operating system are coming to the surface. In this paper, we propose a novel real-time self-defense approach for the Linux operating system, and this approach can be conveniently embedded without requiring the redesign of basic software and hardware platform. The main objectives and contribution of this paper are summarized as follows. Firstly, we present a basic design principle of self-defense approach based on customized Netlink connection. Secondly, we depict the detailed execution procedures of self-defense approach based on customized Netlink connection. Thirdly, we perform a lot of qualitative and quantitative experiments to verify the fine effectiveness of our self-defense approach, and we hope that our approach can bring a feasible opportunity for the cyber security defense of industrial Linux-based devices, especially Linux-based industrial Internet of Things devices. This part is about our approach. In general, the application process is in the Linux operating system can be created by the following two ways. One is the indirect creation by generating an additional process copy, and the other is the direct creation by using the system called exercise. Before executing the native system called exercise, we can monitor and block the new application process. This figure shows the basic design principle of our approach, which contains three significant aspects: Netlink connection, cooperation, and loadable kernel module mechanisms. The main advantage of our approach can be summarized as follows. Based on the above design principle, we further set a trusted listing rules which contains all regular application processes after the system boots. Follow figure shows the main execution procedures of our approach, and the detailed descriptions are listed as follows. Step 1. Load the LPM. Step 2. Establish the customized Netlink connection. Step 3. Monitor each new process creation. And next step, check the new process. Step 5, perform the process handling. Step 6, generate an alarm. Part 3 is about experimental verify and discussion. Various software PLC have been developed to complete industrial process control and automated production. For example, the OpenPLC can run on the Linux operating system to emulate the traditional PLC, which can use Modbus TCP to implement the data acquisition and control management in industrial control communication. And the industrial Internet of Things can use Modbus TCP for industrial control and data transmission too. We install the Modbus TCP master and slave software on the Linux operating system to simulate the Modbus TCP runtime environment. In order to verify the defense effect, we construct a malicious script hackkill to simulate the devastating attack. In this experiment, we respectively perform the same attack with and without our self-defense approach. In this attack, we construct the malicious script. From these figures, we can see that when the system is not protected by our self-defense approach, figure A on the left shows that the malicious script can be unknowingly executed and the Modbus TCP slave process is killed. Differently, when the system is ruled and protected by our self-defense approach, figure B shows that the malicious script can be successfully prevented without disturbing the availability of Modbus TCP application. From the compared results, we can conclude that our self-defense approach can effectively detect our restrict the script-related attack, which use the native Linux script running mechanism. Different from the malicious script, many malware-related attacks always execute the malicious code, which is designed by using some application development language. In order to verify the corresponding defense effect, we develop the malware hypothesis by using the classic Linux C program. Similarly, we also performed the same attack with and without our self-defense approach. From these figures, we can see that the malware hypothesis can be successfully prevented when the system is ruled and protected by our self-defense approach. To sum up, the compared results can offer further proof that our self-defense approach can effectively detect and restrict the malware-related attacks, which develop some malicious application to disturbing various industrial activities. In order to illustrate the advantage of high efficiency, we select the consuming time to handle different process events as an important performance indicator, because an excellent defense approach can take short CPU time to achieve the noticeable protection. Moreover, we compared with a user mode defense approach. For comprehensive analysis, we consider the following in two situations. One is the consuming time comparison for one trusted process event, and other is for one malicious process event. For the above two situations, our self-defense approach can improve the efficiency about 17% and 7%. From the above experimental results, we can conclude that our self-defense approach can obtain the millisecond resolution, which meets the availability of industrial link-based devices and have better real-time performance to protect Linux operating system. In extreme cases, when monitoring each new process creation, our self-defense approach can obtain more current process event, whose application process may be created by released instantaneously. For example, this figure shows that the user mode defense approach only show proc is not exist. The main reason for this case is about the application process has been released and the file system proc has been deleted. In a word, our self-defense approach can provide more effective solutions to protect the industrial link-based devices. Based on the hook operation mechanism, we can further develop a field protection function, which can further prevent an illegal access of some sensitive field. The main execution procedures and the brief descriptions are listed as follows. In order to verify the field protection effect, we suppose that one adversary has successfully penetrated some critical industrial link-based devices and wants to steal confidential information by viewing some sensitive fields. In general, two different methods can be easily carried out to achieve this goal. Linux command and customized malware, like the hack read in our experimental, is a classic Linux C program. We also performed the same attack with and without our field protection function. From this figure, we can see that our approach worked. Both the common Linux commands and the malware hack read cannot be executed to view any sensitive log record, and the terminal can generate an alarm. It's an illegal access. Therefore, the above compared results convincingly demonstrate that our field protection function can effectively protect sensitive information from leaving the confines of normal industrial productions. The last part is about the conclusion. Various Linux operating systems have been widely applied in critical industrial devices, especially Linux-based industrial Internet of Things controllers and gateways, whose vulnerabilities can be exploited by some potential security threats. In order to protect these industrial link-based devices, this paper proposes a real-time self-defense approach based on the customized Netlink connection, which can be easily embedded without the requiring redesign of basic software and hardware platform. On the one hand, the approach can establish the inter-process communication between kernel mode and user mode to enhance the real-time performance. On the other hand, this approach can handle new process events in user mode without affecting the system stability. Additionally, this approach can be further developed to realize a field protection function. All experimental results shows that the proposed self-defense approach can effectively prevent the malware-related attacks and have better efficiency due to the millisecond handling latency. In a word, the proposed self-defense approach can successfully protect industrial link-based devices without disturbing their availabilities. In the end, I would like to express my gratitude to my supervision Wan Ming for his patient guidance and help in this paper. That's all. Thank you for attention.
Hello everyone, my name is Wang Xin. I'm very happy to come here to communicate with you. My research direction is mobile crowd sensing. The title of this paper is Budget Constraint Task Allocation for Mobile Crowd Sensing with Hybrid Participant. Let's start with the background. With the development of mobile devices, mobile crowd sensing is widely used. Mobile devices such as smartphones are carried by mobile users who have the potential to finish the sensing tasks. In the MCS system, the number of mobile users is huge, and multiple mobile users could finish one task together. So mobile users always finish tasks at a low cost. The cost of users is crucial because the platform publishes tasks always with budget constraints. The advantage of low cost means the platform could hire more users to guarantee the quality of sensing data. Because of this advantage of MCS, we can use MCS on some new systems to accomplish tasks like monitoring of water distribution, traffic density estimation, and air pollution inference. As the figure shows, there are two types of participants: mobile participants and static participants. Mobile participants have low cost, large numbers, and flexibility. However, most of the sensing data they submitted are of low quality. On the other hand, static participants, such as city cameras, roadside infrastructure, have low quality sensing data. Despite the benefit of high quality, static participants have less coverage and high cost. Given a budget, the problem is how to assign the task to the two types of participants such that the social welfare is maximized. In these existing solutions, researchers assume the number of users is always adequate. They ignore the situation of rare user participation. Moreover, in the real world, there is more than one kind of participant, but researchers only focus on a single kind of participant. Moreover, mobile users' performance is limited by the personal ability, weather, and the stability of sensors on mobile devices. It is hard to guarantee the quality of sensing data. Accordingly, the task allocation problem is challenging when the number of the mobile user is scarce and most of the mobile users have a low ability to perform tasks. Their studies all consider budget constraints. However, they allocate the budget equally, which cannot guarantee the quality of the sensing task. In our work, we allocate the budget based on Shapley value, avoiding the equilibrium, which makes the budget allocation more reasonable. The main contributions are included as follows. We propose a one-round auction algorithm to select winning buys. Through this algorithm, we could determine which kinds of participants are proper for a certain sensing task. We propose the budget allocation strategy based on Shapley value. We provide different budgets to different sensing areas to guarantee the task finishing probability. Below, I will introduce the MSWPR model. Our goal is to maximize the total social welfare of recruiting participants. The constraint is to ensure that the payment would not exceed the budget. Our recruitment method of our reverse auction mainly include the following 5 steps. The cloud platform publishes sensing tasks in a certain sensing period. Each sensing task needs to be completed within a time interval. After participants receives sensing task information, he will pack his byte price, the task he byte into byte task pair and send to the platform. Then the platform receives the task byte pairing, aiding the participants' historical task completion rate into the task byte pair, forming the task byte completion rate pair. The cloud platform selects the winning byte pair through comparison of the task byte completion rate pair and aids the winning byte pair into the set of winners. After the winner gets the task, he or she starts to perform the task within the time interval. The winner must finish the task before the deadline and send the acquired sensing task date to the cloud platform. The cloud platform receives the sensing task, pays for the participants. The number of unsolved tasks on the sensing platform and the number of low-quality sensing tasks was calculated to calculate the task completion rate of different regions. Next, I will introduce our solution. We propose a utility function, u theta. It represents that the utility of winning byte set theta. In the one-round auction, we choose the participant I with the largest utility value in each iteration, and continue to aid participant I to theta until all tasks are executed. After the iteration, we will get the winning byte set and the remaining task set. The one-round auction algorithm is shown in algorithm 1. During the iteration, we judge whether the utility of the winning byte pair satisfies the needs of the platform. If the conditions are met, we will select the byte pair with the highest margin utility. See line 3. Then we mark the byte user as being recruited. See line 4. Where psi greater than 0, avoid hi equals to 0. Where hi greater than theta, the threshold of task completion probability, we think the participant could provide high-quality sensing data and mark Zij equals to 1. Otherwise, Zij equals to 0. See 5 to 11. We use the second price auction to pay the reward. See line 9 to 10. After selecting the winning byte pair, we need to add the win byte pair to the win byte set phi and update the utility of the winning byte set u phi. Finally, since we only allow the participant I to complete one task in one sensing period, we need to exclude all byte pairs for this participant. Now I introduce our probability calculation of high-quality sensing data method for hybrid participants. For static participants, since the conditions like hardware conditions and operation mode for completing tasks are almost the same each time, completion probability of tasks can be calculated simply by the historical statistics. However, For the mobile participants, it is impossible to use their historical task completion result to make statistics, since the condition of performing tasks may be different each time. In this case, we choose to use the C-Markov mode to predict the participant's ability to provide high-quality sensing data in the current sensing period, so we can get the probability HI that the participant can provide high-quality sensing data in the T round. Now, I introduce our budget allocation method. In the MCS system, we expect participants to provide enough high-quality sensing data in a budget constraint. However, sensing tasks are very sensitive to the location. Some tasks may be difficult and not be completed well. This will seriously affect sensing data quality. For this problem, we use the Shapley value to allocate budget to different regions. We describe how online auction algorithm works in the figure. We added BAS to the ORA algorithm and iterated to achieve the optimal solution. In our online auction algorithm, we calculated the Shapley value of different regions. See line 3 to 7. It is nothing that in the first period, since there is no date of the previous sensing period, we cannot allocate the budget of each region according to the Shapley value. So we allocate the budget of each region equally. Line 5. The winner in each region was calculated using the ORA algorithm, see line 8, and the budget of subregion L is calculated by BAS, see line 7. Now, we perform evaluation of online auction performance. We study task finish probability trend as the number of static participants. The task completion rate of the participants with static participation was significantly higher than that of the participants without static participation. We can see the number of winners from Fig A, in which the number of mobile participants is much higher than that of static participants, because the bid price of mobile participants is much lower than static participants. We can see the average social cost of participants from Fig B. We can see that despite a large number of mobile participants, their social cost is much lower than that of static participants. In this paper, we investigate the problem of task allocation strategy in mobile crowd sensing. First, we recruited participants for and allocate tasks through a one-round auction algorithm. Then, according to the same Markov model, we propose a participant task completion probability prediction for mobile crowd sensing, where the platform could calculate the task completion probability for a certain round auction. Moreover, we propose an online auction algorithm using Shapley value. Through the use of Shapley value, we calculate the task finishing probability on different subregions and reallocate the budget more reasonably. We conduct extensive simulations based on real trace. The result shows that our online algorithm achieves a high task completion rate and one-round auction achieves the highest social welfare. That's all for my speech. Thank you.